What's up, everybody? Roy, this one's for you, buddy. Alright, let's examine what I got going here. I got this little blue mark on the rim indicating the start. So I wanted to map out the poles of all these magnets, So, got my trusty little compass here. This one right here. And it is working properly. It's pointing true north, or magnetic north, whatever. It's pointing north. And let's just take it. Bring it down into the rotor. And let's see what's going on here. Let's see what we got. So, I just checked this a minute ago, and my norths, this is weird. My norths are no longer norths. Where I have marked east and west is now a south. This is weird. Now my east is marked a north. So that's telling me that the fields, it's exactly what I thought. The fields inside the magnets are changing the polarity. They're changing their polarities when introduced to another magnetic field. The magnets are able to change their poles and the direction in which the poles are oriented. So, for instance, this one is marked a south, so I should put it up here and get a south. And this one is no pole. That's why I marked it an east, alright? Because I know there's no east and west. And this one would be the north. And then no pole. And then a south. Because it's a three-phase motor, and I was wondering, so how is it going to be? Is it going to be a north, north, south, south? Because, how would you alternate north and south on a three-phase motor? How would you alternate a dipole three ways? That's the question. That's what I had in my mind. So I wanted to map them out, and that's when I came across the no pole here and here and here. It was a north and a south and a north and a south. So when I check it with my compass, now I'm showing that the south is now facing what I had as west. And my south pole is now no pole, or east. Okay. Are y'all seeing that? Nice and clear? And see, it's because that's the inertia line. That magnet with no pole is actually oriented, the magnetization is oriented to where it's a south facing this south, and it's a north facing the south. It's attracting, and the south facing the north for over here. And that's why this one's no pole, because that inertia line is this way, and on these magnets the inertia line is this way. So what that means, let me find my pen. What that means is that, let's say that one magnet is oriented to where That's the line. That's your inertia line, because it would be south, north. Okay, and that's your line in the middle through the thickness. Well, then that means that the next one, which is the no pole magnet, the inertia line runs up and down. Bam, 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 bam. And if this is your south, if this is your south, then that means this is your north, and this is your south. Because this one would be south, and this one would be north. See what I'm saying? Because check this out. There's my South Pole. There's my North Pole. And in the middle here, along this line, there's no pole. There's no Gauss. There's no magnetism there. That's your inertia line. And I'm saying that the energy travels from east to west, just like a sunrise, just like the sun travels from east to west, okay? And so if you notice, see, it's facing west with my South Pole, North Pole facing outward that way. If I rotate it this way, now it's pointing to the south. The south is facing outward, and we have an east over here, because energy travels from east to west along the inertia line. That's what I'm saying. See? So whenever I'm pointing out a no pole on that, that's what I'm seeing, is the inertia line, no pole, or west. That's what I'm seeing down there. Now then, the magnets have switched back, and now then the south is the north and the east is the west, and the north is the north. And now the west is the west. The south is the south. The east is the east. The north is the north. The west is the west. Golly.